Hello, everyone. Welcome to part one of module one. So this is the first lecture on module one. And after having gone through the syllabus in the previous video, you are now going to go over the start of chapter one in our textbook. And the chapter one in our textbook is on essentially an introduction to thermodynamics. And this introduction starts with the question, what is thermodynamics? So try to pause for a second and think of what thermodynamics is and what it actually means as a word. So thermodynamics is the study of energy. And the study of energy is a very, very broad term. But essentially, we're going to look at what happens to energy when things change. So what happens to energy when things transform? So we're going to look at energy and its transformations. As well as its relations to the properties of matter. So before we continue, just in case you haven't watched the previous lecture, I just want to remind you all that I will be teaching this online as if it were a lecture course. So you can follow along with my notes as you're watching the video. So it's paced so that you can follow along at a reasonable pace. So thermodynamics, going a little bit more into depth about it, it's essentially the science of energy and entropy as well. We'll look at entropy a lot later in the semester, but we can start by thinking of it's the science of energy and entropy. And there's many different definitions, and this is the definition that they use in the textbook. So you might see this definition in the textbook. Now, thermodynamics, the actual word comes from the Greek thermo and dynamics. Thermo means heat. So thermo is essentially equal to heat. And dynamics in Greek is actually equal to the word power. So we're going to be looking at heat and power essentially through thermodynamics. Okay. And what we're going to be defining in this first lecture is a few different terms so that we are all on the same page. So we're going to define a few terms such as system. We're going to define energy, which we already did above. We're going to define properties, what a property means. We're also going to define entropy. And of course, we're going to define heat and power. And this is going to be defined throughout the course. So we're not going to look at all of them today, but it is going to be defined all throughout the course. And we're going to start with the definition of a system first in our class. So this is going to be a definition that we're going to use all the time, and we're going to define our problems and our analysis of thermodynamics through a system. So we're always going to be looking at different types of systems. And a system is just a 3D region of space bounded. So sorry about that. This should say bounded by an arbitrary space. So what does that mean, you would ask me, right? It seems like it's a little bit vague as a definition, but we'll go into it a little bit more. So there are two different types of systems in our thermodynamics class. One is a closed system, and open system. And I want you to try and think of different systems that would be studied in thermodynamics that would be either an open or a closed system. So the more general usually used for a closed system is a piston cylinder assembly. And a piston cylinder assembly as a system looks something like this. So we're going to be drawing a lot of piston cylinders over the semester because this is the simplest system that we can study. And you would have a system that looks something like this. So you would have, our system would be defined by this boundary. So this boundary is called the boundary of control mass. And what we can say is that a closed system is actually called a control mass system. The reason it's called a control mass system is because the mass is constant within the system. You can't take the mass out of the system. The system is completely closed. So usually we have some sort of fluid in here inside the piston cylinder. Okay, so we have a fluid. It could be a gas or a liquid. So this fluid could be a gas or a liquid. And this would be our piston. Okay, so if you want to look up, you can also look up a piston cylinder system if you would want to see what it looks like in real life. And this container here is called our cylinder. And any problem in thermodynamics starts with the selection of a system. So we select the system. And then we usually select the boundaries to the system. And we also select the surroundings to the system. So for example, if we were in a classroom, we could think of the classroom as a control mass system. So a closed system. Let's say we were in a big classroom at FIU. We could say the system is the whole classroom. Okay, that's a system that's closed by a door. We have a finite mass of air in the classroom, and that is our system. Okay, just as if we had a cup of water that was closed or a cup of tea that was closed on the desk, that could be our system, and our classroom could be our surroundings. Okay, so that's the idea behind a control mass system. And the boundary would be the walls of the cup, for example, or the walls of the classroom in the case of the first example. Okay, so that's the first example of a closed system. Now, try to think of what an open system could look like. So let's look at an open system now. So an open system is usually called a control volume system. So not a control mass, but a control. And we'll look at why it's called a control volume. And the simplest control volume system is a fluid flowing. So fluid flowing through a pipe. And so if we have a pipe, for example, like this, so let's say it's like a round pipe with fluid going through, so we could say it's water or air going through. We have air going through, in and out, and we can say, so this is our pipe system, just to have it written down. So we can say that within this pipe, we can segment a little section, so a little boundary. Okay, we're creating a boundary, and this boundary is going to be a boundary of control volume. Okay, so it's going to be a boundary of control volume, and within this boundary of control volume, we have some fluid coming in. So let me zoom in a little bit so that you can see better. So we have some fluid coming in and some fluid out. So now we have essentially a mass flowing in and out of our boundary. Okay, we can see that we have a mass of fluid flowing in and out through the boundary, and the boundary does not move. This boundary of control volume does not move. So it's studying a system that is fixed with a mass going through it. Okay, so that's the example of an open system. Okay, so just to summarize, let me go back to a normal zoom here. So just to summarize, we remember that we can also say that control mass means the mass does not change. Control volume means the mass changes. And the mass changes and crosses the boundary. Okay, so that's very important. The mass continually changes and crosses the boundary. Now, if we think of our system and its surroundings, we can define, in general, we can define that, let's say, an arbitrary system is bound by a boundary, and anything outside the system, so anything here outside the system, is just called the surroundings. And so we can define the system in words as, sorry about that, we can define the system as the quantity of matter or region chosen for the study. Okay, so it's an arbitrary region that we can choose for the study, and it can change. Okay, so we can have a very small system, a very large system, just like we said. If we're in our classroom and we can choose the system to be the whole classroom, and then anywhere outside the classroom to be the surroundings, or we could choose the system to be, let's say, a cup within a classroom. So a water cup within a classroom could be our system, and then the classroom could be the surroundings, for example. So the surroundings is mandatory, but it's just the region outside the system. And finally, the boundary. The boundary is a real or imaginary surface that separates the surroundings from the system. So real or imaginary surface that separates the surroundings and system. And this boundary, since it can be real or imaginary, this boundary is going to be assumed to have 0 thickness. Okay, it's an imaginary thing that we use to see if there's any energy crossing over from it or what could be happening. So, for example, if we had our piston cylinder assembly like this, with our arm for our piston, and we had a fluid in here, we could, for example, since our boundary is, let's do the boundary in orange here. If the boundary in orange is an imaginary line, imaginary surface that's against the walls of the piston, we could say, for example, if we start heating the piston, so let's say we add some heat to the piston cylinder assembly, we now have some heat coming in and crossing the boundary into the system. So the heat is coming from the surroundings, and the heat from the surroundings can heat up the inside of our system. Okay, so we have something going across the boundary. Just like in our pipe example, where we have, so if we look at our control volume now, not our control mass, we have mass crossing the system. So mass is coming in and mass is coming out of our system. So we have something crossing our boundaries from outside our system, from the surroundings, into the system, and then back out of the system. Okay, hopefully that makes sense and is clear. Okay, so just to bring it a little bit further, just to bring the definition a little bit further to understand really what's happening, we can say that an open system, and really this is about defining everything, is a system for which mass and energy may cross the boundaries. Okay, so in addition to mass coming in and mass coming out, we can also have energy coming in. For example, as heat, we can have energy coming in and out of our system as well. So there's 2 different ways in which the energy can be transferred through mass and through energy. Now, for the closed system, you have no mass crosses the boundary. However, energy can definitely cross the boundary in the form of heat, or in another form, which would be in the form of work. So if this piston, for example, so I'll draw it in blue, if this piston starts going down, we might have some energy crossing the boundary in the form of work. So we might have some work being done on the system or by the system on the piston. So we'll look into that a little bit later. Okay, so the next thing I want to go over is some of the physical properties that we're going to look over in this class. So again, this is an introductory lecture. So let's look at some of the physical properties that we're going to be using in this class. And some of them you might have seen in previous courses, but some of them you might not have seen beforehand. So what is a property? The first question is to answer, what is a physical property? A property is any characteristic that can be quantitatively evaluated. So it's any characteristic that can be quantitatively evaluated. So what does that mean, you would say? Well, it means that it's anything that can be measured, okay? And there are many physical properties that can be measured. So try to think about some of them. You can pause the video here, or you can keep going with the video, but try to think of some that you would think would be important and for this course, and some examples of properties. So now I'll give you some of the examples that I was thinking about. So viscosity would be one, for example. And it's not used much in this course, but it's still something that's important. Pressure, this can be used a lot in this course. Volume, okay, we can measure pressure, we can measure volume, we can measure density, we can measure temperature, we can also measure mass. And then there's some more too that I'm not going to list, but such as a little bit more detailed. So electric conductivity, thermal coefficient of expansion as well, could be other ones. And the value of the properties. So the value of these properties is what defines a state. So the value of a property defines a state of a system. And what do we mean by state? We just mean that the state is a condition of the system that is characterized by the value of its properties. So I'll just write it down because I want everyone to have the definition, and this will be in your available notes on module 1. So I want you to have it. Is condition of the system characterized by the value of its properties. So a state is essentially just a moment in time where we look at a snapshot of a system. So let's say we have, once again, our piston cylinder, and I'm just gonna have the piston like this. I'm not gonna do the arm every time on the piston, but you should know that this is the piston and this is the cylinder. So it's a piston cylinder assembly, and we're gonna be using those a lot. So essentially the state of the system can be, for example, defined by pressure, volume, and temperature. Okay, so our pressure could be, for example, 100 kilopascals. And our temperature could be 300 Kelvin. And our volume could be 1 meters cubed or cubic meter. Okay, that's a state. And what we are going to be looking at is what happens when there is a change of state. So for example, this could be defined as state 1. So state 1 would be pressure 1, volume 1, and temperature 1 are the following values. And then let's say we start adding heat to the system. Let's say we start adding heat from the surroundings to the system. What's going to happen is we're going to have our control mass here. And all of a sudden, we might have state 2 with different values. So pressure 2 would, for example, still be equal to 100 kilopascals. But now, volume 2 is now equal to 2 meters cubed, because we know when we heat something, it usually expands. And temperature 2 might go up because of the expansion, because of the increase in temperature from the heat put into the system. So this is the definition of state 1 and state 2. So it's a state, a condition of a system characterized by the value of its properties. A state is not liquid, gas, or solid. Okay, so make sure you do not confuse that, because a lot of people will confuse what is a state of a system. Oh, it's a liquid or it's a gas. This is not correct. A state is not a definition of what the system looks like in terms of its physical composition. Okay, it's just defined by the different values of the properties. Okay, so it's just defined by its properties. And you can have as many properties as you want. So you could have mass 1, you could have density 1. All these different things could be added to the system definition. Okay, and to define a state, you need a certain number, and we'll talk about that a little bit later. So now, since we started talking about liquid, solid, or gas, the next thing I want to define is a phase. What is a phase? The phase is the quantity of matter. So it's a quantity of matter that is homogeneous throughout, in both chemical composition and physical structure. So what does that mean? That means that, for example, if we have water and we want to define the phase of water, there are 3 different phases that can exist. So water can exist in 3 phases. And you should be able to know these phases, but the 3 different phases are liquid, solid, and vapor or sometimes also called gas. Okay, but for water, we usually call it vapor. Okay, and a system, so a phase is just one of those three, right? One phase is either liquid, solid, or vapor. However, a system can have multiple phases at once. So a system can have multiple phases at once. And just let me write this T and I again. So what does that mean? That means that theoretically, what could happen is, let's say we have a box, okay, a 3D box of mass. So there's no mass escaping or coming in. Okay, so this is our boundary. Okay, this is the boundary of our system. And let's say we have water in here. And what could happen is we could have some heat added to the water. So we could, for example, have some heat added to the water. We have heat added to the water. Well, what happens is you could have, so let's say this was liquid water to start with. And in a second instance, we're going to add heat. This liquid water is going to transform into something like this, possibly. So you might have now a two-phase system where you have liquid water at the bottom still. And you also have vapor at the top. And now you have essentially two different phases within the same system. Okay, and we still use the same control mass. I'm just showing you how to separate them between the two. So now there might be a percentage of vapor. So let's say 50% vapor and 50% liquid. Now, in real, when you use a pressure, or even when you cook your pasta and you put the lid on, you see there's a lot of steam, but there's still liquid water as well. When the water's boiling, it doesn't all immediately become vapor. The vapor sort of becomes more and more and more vapor, and the water gets less and less and less liquid. But it takes time. It doesn't happen instantly. So when you add heat to water, you can have two phases point in time. Okay, and a good example of that is when you're boiling pasta or you're cooking rice or anything like that. Okay, so now let's go over to the definition of a process. So how can we define a process? A process is any change that a system undergoes from one state to another. Okay, so it's any change that a system undergoes from one state to another. Okay, so a process is a change. It's a change because of something happening to the system. And the path of that process, so what we usually call the path, is a series of states through which a system passes. Okay, so what does that mean? Let's say we have some sort of process. Let's say we have a process that is occurring. Let's take a piston cylinder assembly and let's look at it and look at what could happen. So let's say we have a piston cylinder, and I'm going to put it sideways just for illustration purposes. So we have a piston cylinder with a piston starting here, and our system is defined by the boundary drawn above, which is going to be on the surface of where the limit of the mass is. And this is going to be a control mass system. Okay, no mass can exit or come in. So it's a control mass system or a closed system. Okay, just to get used to the fact that a piston cylinder is a closed system. Okay, and we'll look later on in class at piston cylinder systems that are open as well, but for now you can think of them as a closed system. Now, in part one, so state one is this state right here. And for state one, we have a certain pressure, volume, and which would be P1, V1, and T1, for example. Okay, so we write all our thermodynamic properties down. And then we're told that our piston cylinder is actually our piston is going to move new position down this way. So it's going to move to a new position down this way to a new point. And this new point is going to be called point 2. So now our same system still has the same mass. Okay, but now our piston has compressed the liquid fluid inside. Okay, so let's assume the fluid is air just for ease. So the air is compressed to a certain amount. And now, so this should have said state 1, sorry about that. And now state 2, so let me write it in green, state 2 is defined by pressure 2, volume 2, temperature 2. Now, state 2, let's talk about state 2 and sort of analyze it a little bit. Would the pressure of be greater or smaller than 1? If we compress from 1 to 2. And again, these are assumptions, okay? We're just assuming what could happen. So let's say we have pressure 1, volume 1, temperature 1, and mass 1. And we're looking at if pressure 2, volume 2, temperature 2, or mass 2 are greater than or less than pressure 1, etc. So let me just move this around so I can illustrate a point after. So I'm going to move this to a different place just so we have it here on the side. And let's look at what this could be. So if we compress air and we press air into a smaller volume, what happens to the pressure? Pressure 2 is going to be usually greater than pressure 1. What happens to the volume? The volume we can actually calculate just by looking at it, right? If we look at volume of 1, the volume of 1 is this whole area here. Okay, so that's the whole volume of 1. So volume 1 is way bigger than volume 2, which is just in this little box right here. Okay, so volume 2 is going to be less than volume 1. What about temperature? Well, usually when we compress something by putting work on it, by pushing it into a smaller space, what happens is the temperature usually increases. Now, this is not always the case because there might be some heat being lost in the system, but we can assume for now that temperature 2 would be higher. Okay, we're not sure, but we can assume that. What would happen to the mass? Does the mass change between 1 and 2? No, it does not. the mass stays the same. It's a closed system. Okay, we just moved the piston down, but we didn't get some air out of the system or anything like that. We just compressed the air, hence why the pressure increased. So now what we can do is we can take this system, and I'm just going to erase these two lines that I drew for the system just so that we have a better view of the system. But what we can do is we can have a process diagram drawn between the two different states. So we have state 1 and state 2. And we know that state 1 starts at a certain pressure. So it's a PV diagram. Okay, so we're using a PV diagram now. So it's a diagram of pressure versus volume. And we can say that at state 1, the system has a pressure of 1. And the volume, we can actually directly write down from our diagram as V1 like this. And then we can see that V2 is directly below this line here. Okay, so that would be V2. And now we have pressure 1 and V1, and we can intersect them together. So they intersect at this point. So this is our original operating point. This is point 1 on a PV diagram. Okay, the pressure and the volume are defined by point 1. This is essentially state 1. What about state 2? Where is the pressure going to be in state 2? Well, we said the pressure was going to be higher. So the pressure at 2 is going to be somewhere here. And again, this is just an example to illustrate. It's not actual values, but the pressure 2 would be higher. And it would intersect with volume 2 here. So now our new operating point for point 2 is here. Okay. And from that, we can see that we now have a process from 1 to 2 by pushing that cylinder. So if we look back at our definition of process, a process is any change that the system undergoes from one state to another. The system went from state 1 to state 2, where the piston essentially compressed the air. And by compressing the air, it reduced the volume and increased the pressure. Now the path is the series of states which a system passes. So between 1 and 2, there's actually an infinite number of states in between, right? If you move, let's say instead of moving the piston cylinder all the way, we move the piston cylinder to this point here, we would now have an extra state defined by, let's say this would be B, for example. It's an intermediate state. Path is the sum of all these little states put together. And so I'm just going to erase this so it doesn't confuse at the end. But essentially, what we do get is we get a certain path on which the state 1 goes to state 2. So usually something like, okay, so we have a path to define the process. So the process is essentially the process going from state 1 to state 2. The path is the line in which it is achieved. Okay, so it's as if you had a bunch of different intermediate states which you went through to go from 1 to 2. Okay, it's a constantly changing system, and the process is just a start point and the end point. So this is start and end. And this is looking at the process through the change. Okay, it'll become clear once we do examples and all of that too. So that shouldn't be a. So we're gonna actually stop it here for today, for this particular, not for today, but for this first part of module 1. So we'll put processes and cycles in the next part. So this is our first part of module 1, and we will go into part 2 of module 1 in the next video, where we will continue with our process and then look at cycles. So we'll start with the same diagram of the process from 1 to 2, just simplify. So our 1 to 2 is right here. We'll look at the process from 1 to 2 simplified and explain the system. And then we'll go a little bit more into more definitions for the class. So this first chapter is mostly about definitions, and that's what's important to know. I will see you in the next lecture. And if you have any questions, do not hesitate to contact me in the ways described in the syllabus. Thank you.